time for us to start. I hope actually I'm audible to all of you. It's okay? Thank you.
Sir.
Yes.
Very good afternoon to all of you who have joined here to listen to the 55th distinguished lecture being organized by INA Bhubaneswar chapter, IIT Bhubaneswar,
কি ডেটটা কবে আছে ছবিটা?
IMMT Bhubaneswar,
24/2/25 এর নেটে করে দাও।
Nizer Bhubaneswar, Sikha Anusandhan University, then of course IEEE Bhubaneswar section. So today our esteemed speaker is Professor Sarit Kumar Das. He is a Institute Professor, Indian Institute of Technology, Madras, Chennai, at Chennai. And his topic will be revitalizing nanofluids, 3 decades of evolution, challenges and breakthroughs in thermal management and beyond. Of course, I'm not going into the abstract of what he has given. It is already circulated to you. Very interesting topic and lot of insight definitely will get. Now, so far as Professor Sarit Kumar Das concerned, he is an institute professor at the Indian Institute of Technology, Madras. He is the first occupant of V. Balakrishnan Chair Professorship and a Professor of Mechanical Engineering Department of the Institute. He is the former Director of Indian Institute of Technology, Ropar. He is also the former Dean Academic and Research of IIT Madras. Professor Das studied at the Jadavpur University and did his bachelor's degree in 1984 and master's degree in 1987. He did his PhD from NIT Rourkela, my alma mater, in 1994, and he was Helmut Schmidt University at Hamburg, Germany as PDF. His recent group works on various aspects of thermofluidics like heat and mass transfer in industrial equipment such as heat exchanger and fuel cells, multiphase flow and energy conversion. The group focuses explicitly on micro nanoscale processes and is known as to be one of the leading groups on nanofluidics in the world. Another area of focus of this group is bio-nanofluidics to medical diagnostics, the platform of drug delivery and understanding pathological states related to cardiovascular diseases and cancer. Professor Das is a fellow of the National Academy of Science, NASI, and Indian National Academy of Engineering, as well as the Alexander von Humboldt Foundation. He was a visiting professor at MIT, Cambridge, and a visiting professor in Lund University, Sweden. He is conferred with the prestigious India Citation Awards of 2012 by Thomson Reuters. He has published more than 370 research articles and 6 books. He is most cited.
নতুন মিনিস্ট্রি তৈরি
He
করে
is most cited.
আইআইটি থেকে ডক্টরেট করছেন না, তাদেরকে দিচ্ছেন একটা ফরেন ডিজিটাল।
There is some noise anyway. He is the most cited mechanical engineer of the country. Professor Das is a member of the editorial board of Heat Transfer Engineering, Taylor and Francis, publisher, and the former editor-in-chief of the International Journal of Nano-Scale Transport. He received Lifetime Achievement Award from his institute, IIT Madras. With this brief introduction of Professor Das, I will now request our two co-sponsors actually who are there, SOA University and IEEE Bhubaneswar section, to say a few words, and then we'll request Professor Das to make his presentation. Professor Nanda, please.
Sir. Thank you, sir. Good afternoon, Honorable Chairman of this IIT Bhubaneswar chapter, as well as also Chairman of our Advisory Board of SOA University. And today's distinguished speaker, Professor Sarit Das, who is currently the Chair Professor at IIT Madras. Also, we are together for some time. It's nice meeting you after a long time. And all the distinguished members and fellows of the INE, and ladies and gentlemen. So at the outset, I must once again welcome on behalf of SOA University as well as all other co-sponsors, our esteemed speaker, Professor Das. Our university currently is having 13 institutes offering in 10 disciplines, right, starting from engineering, medicine, healthcare sector. This year we have opened 2024 we have opened a new medical college, and also dental college and veterinary institute 2022, and also a nursing college and a pharmacy institute. And we have also a hospital at Berhampur. And because of this, we have been ranked in the QS Asia ranking 278 this time. And our NIR ranking is 14th in the university category, engineering is 26th, and medical is 21st, and dental and law, they are in 10th, 9th position. And our management is 62th position. And as far as the THE ranking is concerned, we are 800 to 1000 world university ranking bracket, and 300 to 350 our THE Asia ranking. And this is about our ranking. We have 18,000 students, 1,740 faculty members. We have 60 research labs, 20 research centers, and we have 1,300 research scholars, and 2,000 PG students and all. So this is brief about our university. We are happy to host this co-sponsor for this kind of the INE lecture series, and listening to all the distinguished speakers across different disciplines. Thank you, sir.
Thank you, Professor Nanda. May I now request Mr. Tripathi to say a few words about IEEE Bhubaneswar section. It became a section only a few days back. Tripathi sir,
okay, I'll come back. Yeah. Good afternoon to everyone. Thank you, Dr. Acharya, for giving an opportunity. At Bhubaneswar, we have got roughly about 100 engineering colleges, and IEEE activity started in 2014-15. We were given a status of subsection, and from there we had several societies started. Today we are a section, full section in Bhubaneswar, and we have got 11 societies and associations and 17 student branches. Am I audible, sir?
Yes.
Yeah. Thank you. And we have got a very strong base here, and we are conducting executive council meetings regularly. Earlier we were a branch of Calcutta. Today we are independent, and we have got a very active group working. Once I was the chairman, now Dr. Subhranshu from IIT Bhubaneswar is the chairman, and the activities are various. Number of activities are so tight that we don't have a time to make another event in this year. We are postponing the events to 2026. The whole year is packed in advance, and we had conducted several IEEE milestone seminars, and with the help of SOA University, with ITR, with KIT, with Silicon, and all the universities around, including CB Raman, OUAT, they are active members and they are contributing. And thank you, Dr. Acharya, for opening this platform to also IEEE members. I think we are fully participating in this joint venture. Thank you.
Thank you so much, Mr. Tripathi sir. Now, may I request Professor Das to please make a presentation. And for your information, it is being recorded. And if you permit only, it could be shared with others.
Yeah, it can be recorded, sure.
Okay, thank you.
Are you able to see the slide?
Absolutely.
Just a little adjustment here. So today I'm going to talk about a very specialized topic, revitalizing the research in nanofluids. This particular area started about 25 years back. It went through an up and down and upsurge once again. So before doing that, let me first thank the INA Bhubaneswar chapter for inviting me for this talk. I'm happy for two reasons. Firstly, I've been an INA fellow since 2007, so I always feel good to come back to INA events. The other reason is my connection with Odisha. 7 years I stayed in NIT Rourkela, and my research career actually started there only. Even yesterday, I talked to my guide, Professor R.K. Sahu, and hence that connection is still there. In fact, even my ODI is fairly good. So whenever I get chance, I try to communicate. Now, coming to, and today, as a result of that, I see even in the audience today, many of my friends, teachers are there. So I'm extremely happy for this. Now, coming to this particular topic, I will come to the topic just a moment later, but it doesn't talk of just one topic, nanofluid. It talks of a general trend in technology development, which happens to every field. There are two paths of growth of a technology. Some technologies, after the initial promises, they grow exponentially without any stop. The greatest example is probably electronics, which started with vacuum tubes. At that point of time, very few knew what is the prospect. But you look today, it has grown and grown and grown over last probably 70, 80 years. It has grown unstopped. Look at computer science, another regime. With great potential, it has grown, and we are now thinking of everything based on computation, even at a greater level with quantum computing peeping at the corner. Biotechnology, it started, well, we had always biology, but from tissue culture to cell manipulation to everything, it started probably 30, 40 years back, and it is unstoppable. Automation, there's no end to it. Today's AI is half automation driven. And today people are saying that AI will be like that. I have put a question mark there because we really don't know. Why I tell that? Because there is another list on the right-hand side. Not that every technology, when it develops, it goes, unstopped exponentially. There are certain technologies which show a lot of promise at the beginning, but then we find that all the promises are not fulfilled. And quite often, they become successful only in a narrow area, only in one kind of application, only in certain aspects. For example, superconductivity. When we started our career in 1980s, Everywhere, the buzzword was superconductivity. Consecutively, 3 or 4 times Nobel Prize went to superconductivity. I remember my first conference that I attended was in IIT Kharagpur. It was the National Cryogenic Conference. And what happened? The cryogenic system people like us were given a small room. The huge auditorium was full of people who were only doing superconductivity. But where is it now? People have somehow realized that superconductivity at normal temperature is unattainable. So it has died down. But superconductivity as a discipline still is an active discipline, but the goals have changed. Superconductivity is now for superconducting magnets, for maybe even quantum computing, low temperature production, study of molecules at extremely lower temperature, Bose-Einstein condensation and things like that. It has restricted its fields to a smaller one, but there, of course, it is successful, but not at the global level as it was thought. Previously thought all the transmission lines will be superconducting and all that. That didn't happen. You take another nanotechnology. Oh, there was so much hype even 10, 15 years back. Today, what has happened? It has diffused into different fields. So nanotechnology as a thrust at that level, probably it does not exist. It has been absorbed in various, other technologies, and it has become very normal ways. There was a time CFD or computational fluid dynamics. Everybody working in thermal was working with CFD. Now, where is the CFD community today? The thing is that CFD has become all highly sophisticated, software driven. And as a result of that, what has happened? Now, CFD, what was at our time when we were doing PhD, what was a PhD problem in CFD? Today, that is an undergraduate assignment. You give it to a student, within 7 days, the student will give exactly the same results using all the softwares. So, it can happen even to AI. We are talking of algorithms, these, that. It may be that 20 years later, all those AI algorithms will be in your smartphone, and you don't even need to do any research on that. So all the technologies don't grow in the same way. Certain technologies find out newer and newer applications. Certain technologies do not. Certain technologies, they go through an up, and then its restrictions, its limitations are discovered, and they limit into certain regions of applications. Now, I think nanofluid is such a technology, and excuse me, I think someone's speaker is on. Yeah, in Bengali, somebody is talking. Please switch off the speaker. Yeah. So next, look at what is the real motivation of this technology, nanofluid. We know the well-known Moore's law that every 2 years or 18 months, to be precise, the number of components in an IC chip doubles. Moore gave this law in 1965. Fortunately, even till today, it has continued. But we are seeing serious difficulties with this law. It appears that it cannot grow anymore following this law. The reason being that the equipment becomes so small that the heat generation, thermal fluctuations are trying to disrupt the activities of the chips. And hence, cooling of electronic equipment for the last 20 years or so has become a very, very important area. If we look the same thing from a different angle, which is power density, not just look at the number of components, your chip may be taking 5 watts or 10 watts, but if you look at the rate at which the cross section is decreasing, now we have got 23 nanometer, 19 nanometer, 18 nanometer devices, And if you take out that area, actually in the electronic chip, today the heat flux is so high. Actually, it is shown only up to 2010. Today, the heat flux has crossed that of rocket nozzles. So, how to manage the electronic equipment is one of the major reasons for going for new cooling technologies. Now, coming to the next one, I will now go to the, excuse me, I will go off for a second and come back. There is some problem in the presentation. Stop sharing. No. Are you able to see now?
Yes, sir, we
Yeah.
can see. Yes, sir.
Yeah, there was some technical hitch here, so I'm coming back once. Okay. Now, going to the next one, what nanofluids are? Nanofluids are basically fluids of nanoparticles suspended in normal liquids, normal Newtonian liquids, water, maybe water, ethylene glycol, maybe alcohols and so on, but nanoparticles which are suspended into it. It came around 1999, 98, 99, around that time it was first time proposed. And that time it was thought that it can go to cooling of electronic equipment, electric and hybrid vehicles, surgery, solid propellants in rockets, fuel cells, MEMS, metalworking, solar energy collected, and so on. How it has been successful, I will come to that in the application part of the lecture. But first, let us say, what is nanofluid? It's not moving. Yeah. When two immiscible fluids, particles and liquids are mixed, we call it a suspension. Generally, smaller size particles suspended in liquids are said colloidal suspensions or dispersion. But nanofluids may be defined as a special kind of colloids which are very dilute. So 2 points are important. Very dilute. What is the kind of dilution? We are talking of suspensions of less than 1% concentration of the particles. 1% by weight, even volume can be even less than that. And as a result of that, the fluids remain Newtonian. So fluids remain just like, it behaves somewhat like water, but its properties get changed. And what is that change? Why we use such suspensions for cooling, the reason is very simple. that usually all the coolants that we use, including the best one, which is water, the thermal conductivity of our coolants are very poor. You just try to compare the thermal conductivity of various particles. Say, for example, thermal conductivity of copper is 500 watts per meter Kelvin. That of aluminium is nearly 350, 400. That of even the worst one, which is stainless steel, is about 25. Whereas the thermal conductivity of water is only 0.6 watts per meter Kelvin. And that of air is 0.01, which is almost insulating. And hence, whatever technology we may use, our cooling technology uses air, water, the thermal conductivity itself is bad. It is something like, you want to fly from Bhubaneswar to Delhi. Now, you are choosing the flight which goes fastest. That's fine. But what is the use of using the faster flight if you have to start from your home and the traffic to the airport itself takes you to 3 hours? Similarly, when we cool anything with a liquid or a gas, if the conductivity of the liquid or the gas itself is poor, then it doesn't matter what kind of cooling technique, equipment, etc. you use, your cooling is going to be poor. And that's the reason we have this problem of using any of the existing liquid or gases. Now, so people thought how we can improve the conductivity of the liquid or the gases. And they thought of the suspensions. It's not that we are thinking of suspension today. In fact, the first time use of suspension for various electrical as well as thermal applications was thought by Maxwell, which is more than a century back. But then there are some certain problems with usual suspensions. First thing is sedimentation. They sediment after some time in circulation, they settle down. They create fouling of the apparatus. Apparatus gets coated with those particles. They clog the passages, valves, and so on. And because those particles transfer momentum to the surfaces, there is erosion of pipeline, erosion of pumps, valves, etc. Of course, you have to pump the liquid along with the solid particles, and so pressure drop increases. And then we get moderate enhancement depending on volume fraction. That means more the solid volume fractions, more is the conductivity, but more is the problems which I have told earlier. On the other hand, nanofluids, it's a very stable suspension. Because the particles are smaller, they remain suspended. Of course, there are certain techniques to do that, but they remain more or less suspended on the liquid. The fouling is very less because you are using very less amount, less than 1%. There's no clogging we have seen so far. Erosion, because the particles are nanoparticles, so the momentum transferred to the solid is so less that the erosion is negligible. Very minor increase in pressure drop because the amount of particle is very small, and high enhancement, which does not depend only on particle size, on particle concentration or particle volume fraction, but it depends on particle size. I will come to this one later. That smaller the size, more is the enhancement of conductivity. Now, how these nanofluids are made, you can see there are various methods. One of the methods is, while synthesizing the particle itself, you make the nanofluids. That is what is known as one-step process. But I will be talking about the two-step process, which is the most common one. You take a base fluid, you take nanoparticle, you mix them. Of course, mixing them will not make it a nanofluid because lumps of the nanoparticles will be there. You have to break the lumps. Usually what is done, you have been shown here in this particular, ultrasonic vibrator, that ultrasonic vibration is one of the methods by which we stabilize. We also add certain things to stabilize so that they remain stabilized. One of the ways of doing it is adding, adjusting what is called the pH of the solution, and the dispersion is stable when the zeta potential values, and zeta potential actually indicate the electric double layers around the particles. Because the particles are so small, they are always electrically charged, because outside shell there are double layer of electricity, and if they are repelling each other, then it remains very stable, and that can be ensured only when they are of zeta potentials of more than 30 millivolt or less than minus 30 millivolt. Now, if we do that, this is the zeta potential measurement, and as the total counts of the particles. And looking at that, before centrifugation and adding acids or adding surfactants or adding stabilizing materials, before how they remain as a lump, and after that how they became dispersed uniformly, it is shown here. 11 nanometer, 45 nanometer, and 150 nanometer, 3 types of particles of aluminum oxide has been shown here. Now, with this introduction to nanofluids, let us look at some fundamental studies which were made with nanofluids. First thing is, like any other concentrations, it was shown that with volume fraction, the conductivity goes up. This is nothing new. As I said, Maxwell itself said this 100 years back. He even gave an equation how to calculate the effective conductivity. Of course, he was looking for electrical conductivity, but in the process, he also predicted the thermal conductivity. Now, that is nothing new. But what is new is the second figure, where you see as the particle sizes go down, you see the percentage enhancement of thermal conductivity of the liquid goes up. That means that 150 nanometer, if the enhancement at a particular concentration, 1% concentration, is 3%, at 50 nanometer, it becomes 6%. And at, say, 20 nanometers, it becomes 25%. So this was the main inspiration behind having nanofluids, putting nanoparticles into fluids. This was done by a group in Argonne National Laboratory, led by Dr. Choi, a Korean-American person, who named it as nanofluids. And it was found that if we can make the particles smaller and smaller, the enhancement becomes more and more. Now, and this, it was also found that the classical suspension theory and Maxwell's equation do not work here. They are more than that one. Now, why it happens? That is the time I entered into this particular field, and I looked at, if it is happening, there must be some kind of motion of the particles, because the particles are so small, maybe Brownian kind of a motion. Now, how can I measure those Brownian kind of motion? It's very difficult to have nanoparticles making Brownian motion to really make measurement. I went in a different way. I said Brownian motion depends on temperature. You see, if I increase the suspension temperature from 20 degree to 50 degree, just here you can see in the third picture from 21 degree, which is the room temperature, because this was done first time by me at Germany. So there the room temperature was 21 degree, and we heated up to 51 degree. You can see the enhancement became 3 times. What was 5%